Well, let's be start again. Today we're going to speak about NMR. So NMR, I don't really care if you get the right answer or not. It does not matter. I hope I'm being clear about this. If you get the right answer but your logic is wrong, you're still gonna lose most of the marks. If your logic is correct, but then when you combine them together, you get the final molecule wrong, you still get most of the marks. Okay, so welcome everyone. Janine, Francesca, Justine, Krista, Maria, Maria, Sam, and Janice. I hope those who had psychology yesterday, you did well. Now, if you have physics, it's fine. It's not the end of the world. Tomorrow, just focus on physics. I will give you a day off for chemistry, no. But if you have physics, tomorrow is Saturday, focus on physics, and then you have some catch up to do. But by today, we should be in a position where you're covered. You would have covered everything. I uploaded the videos for the synthesis yesterday. Question 19, you couldn't work. Okay? I didn't even try to answer it. I tried to answer it and I realized I made a mistake with the name for the final product. You could answer it, so if you actually try, there are ways how to answer it. Primarily, thinking about it now, I think you can use the Grignard. Um, but leave it. Okay? So if you could use the Grignard, maybe I'll edit it and do it later. NMR, it's about describing the information. It's about analyzing the information. So NMR, you're gonna understand if you have singlets, doublets, triplets, and quartets. If you have singlets, doublets, triplets, and quartets, NMR is actually very useful. Why am I advising this? Because for NMR, okay, the most important concept is understanding the environment of the hydrogens and what they're adjacent to. Singlet means it has no adjacent hydrogens. Doublet, it has one. Triplet, it has two. Quartet, it has three. Sometimes you can see quintets, sextets, septets. These are very rare. Especially these are very rare to be perfectly neat. In fact, when we look at real NMRs, okay, you start seeing something like this. This is a perfect sextet. So this would be you have five adjacent hydrogens, but it's not that common. Okay? It could also mean other things. It could also mean that you have certain splittings. Okay? Certain adjacent schismom. Most of the time, certain adjacent hydrogens, so it would be 2 and 3. But most of the time, when you have adjacent hydrogens, you have CH3, CH2, CH2. The middle CH2, you CMS. So this we consider to be a multiplet. Apart from this, these also, or certain patterns, are also very important. A triplet next to a quartet is this CH3, CH2. Triplet and triplet next to each other, CH2 and CH2. Singlet, it must be a CH3. It can be anything depending on the integration, but singlet normally it's the end CH3. Doublets are the rarest. Because doublets, you're saying that you have only one hydrogen next to it, which is possible. Okay? Which is possible, so don't get me wrong. But this, together with this information, you'll be able to analyze and work on most molecules. Now, what I'm gonna do this morning is I have to find one that I didn't actually give you. Now, I could have worked that one. I don't think I gave you anything with bromines, so this is fine. Again, I want to work different ones. I want to work two different ones because I actually want to show you how to do this. Okay? By the way, I realized that some of the questions I gave you yesterday weren't really three steps, they were like four or five. Apologies. Um, The three-step process in my mind was you have to go from here to there to there, which was fine. But sometimes, for example, if you have always carboxylic acid being formed in your DNA08, you must go to the carboxylate first, which is a step on its own. It doesn't really matter. It's a step on its own that's gonna be pretty much 100% successful. Imma, it's a step. Metsec don't really mind, by the way. Metsec, when you have a NaOH reaction, whilst it's considered to be a step, they won't reduce marks. Okay, now this was cis3H6Br2, and here we need to start thinking about what we've got. So, first and foremost, the integration looks off. The integration looks off because it's 1 and 1.7. Now, 1 and 1.7, it should not be. So I'm gonna ignore the integration for now. Okay, I'm going to ignore the integration and look at this. Okay, so I'm gonna ignore the integration and look at this. So this is a triplet, this is a quintet. You won't know it's a quintet. Again, mostly you're gonna see it in a quartet. So it's more than 3. So when I look at this, I tend to round that to 2. And it makes sense. It makes sense because if I round that to 2, then it's 2 and 1. If I multiply everything by 2, it becomes 4 and 2, which is equivalent to the 6 hydrogens I have here. There are only 2 peaks, not 3, so this must be a symmetrical molecule. And if I'm gonna draw that as a symmetrical molecule, there are 2 options. CH3, CH3, Br, Br, or CH2, Br, CH2, CH2Br. And this is the correct answer. It's correct answer why. So first and foremost, I have this peak here, which is a CH2. Apologies. Sorry. I have this peak here, which is a CH2. Okay. And I also have a peak that is a triplet, meaning it's next to 2 hydrogens. So these 2 hydrogens are gonna influence that, and they're gonna influence that. But each of these 2 peaks is going to be the same, so it's gonna appear as one peak. Okay, so it's symmetrical, so these CH2s are the same, and they are both adjacent to a CH2, meaning that is the right structure. If you are unsure, okay, here you can actually draw the bonds and try it. Okay, I had sent you this. I will send it again. I think it's like this. Tipo, I think it's fun. Don't waste too much time on it. Okay, but I think it's a little bit of fun. The snow. No. This is an interesting one for you. Okay, it's 2 carbons, H4O2. Why is it interesting? Because this, you have the CH3, therefore, sorry, 3 and the singlet, therefore it's CH3 on its own. You have 2 oxygens, but it's this one up here. If we were to look at these values, I don't even think you have a value. There, here. 11 to 12, it is the carboxylic acid. So you will have a carboxylic acid. So in fact, this molecule, okay, and it makes sense. Look, CH3, C, OOH. And when you remove the CH3, and this is something I do. When I remove the CH3, what do I have left? And this is simply CH3 COOH. Okay, so take it, it's a challenge. These questions tend to have a lot of marks. The I'm trying to avoid to go through um, fluorines and chlorines, okay? One halogen is fine, but fluorine is not one that you have. This is ethane dioic acid. How do I know? I recognize the structure. Sometimes when you see a structure, you already know what the molecule will be. Nitrogen we avoid. I'm avoiding benzene ring because you've never had benzene rings. So these are all benzene rings. Benzene. There's benzene there, there's benzene. Probably not benzene, but possibly actually yes. Doesn't mean they are hard, but it makes life a little bit more complicated. This, again, it's also possibly possible. It's 6H15 and you have an NH2, and it's trying to identify what the peaks are, but it would be a bit on the difficult side, especially for MedSec. But this we can do. Now, this looks as if it's hard, yet it should be fine. Now, the first thing I will note is there are 5 hydrogens, there are 10 hydrogens on top, so these are multiplied by 2. Okay, that must be SCH2, that must be SCH3. This is a quartet, so it must be next to SCH3. This looks like a triplet, okay, but there are other things. In fact, even here there seems to be another impurity, so this must be a CH3 CH2 and CH3 CH2. Because the number of peaks are what they are, it must also be that they are symmetrical. When you take a look at the value, okay, it's at 2.5. 2.5, we're gonna see that that's gonna be next to a carbonyl or an ester. So when you look, so this, okay, must be next to a carbonyl. So when you actually, now this I actually love telling students. I'm gonna do the double bond O at the bottom. So when you actually see what's left, all the carbons are taken, or the hydrogens are taken, so what's left is an oxygen. So these two must be connected through an oxygen. And this is an acid anhydride. Okay, now normally for things like this, for acid anhydride, for these kind of reactions, when they give them in exams, they tell you this product will then react with water to form acid, or this product is formed through, or this product is used for this reaction. Okay, but all I did here was identify what needs to be done. In fact, this product makes sense that it's gonna have the small peaks here and a few more peaks there, because this product will probably hydrolyze with the water in the air to form carboxylic acid, which is a little bit less downshift. Okay? And again, if you are unsure, You draw it. And it's marked as correct. Let's see if this is another one which is very similar. Okay, again, you have the CH3, CH2. I don't even want to go into this because this molecule you wouldn't have. This molecule, from what I'm seeing, no. Carbon, carbon, carbon. Oxygen, carbon, carbon, oxygen. From what I'm seeing, that one is this. C6. Okay. Um, so this structure, I would find it very, very difficult for them to give you. Is that this structure here, it is ethane dioic acid. So if we were to just go here, it's the oxalic acid or oxalate as used in the practicals. But again, I would say they would be relatively harsh on you if they were to give you that. Here you have a benzene ring, benzene ring. So again, for what I want from you is to identify all the groups. This I want to work. This is a lovely one. C5H10O. Mela, first and foremost, when we see something like these, just consider them as doublets. Okay? Also, here I tend to take a look and realize that a 6, when you see this peak, I'm marking it because normally it will disappear. That's an OH. So this must be CH3 and CH3. Both are okay. Both are um, singlets. So doublet and doublet. Okay, and this is a CH. But dawk huma CH. So these are CH and CH. This is also a CH, and it's very possibly, I'm not even gonna identify what that peak is. I will call it a multiplet for now. Okay? I will simply call it a multiplet. Now, so when we look count the hydrogens, you have CH3, CH3, 6, 7, 8, 9, 10, which seems to be correct. C5H10, okay, that would be an alkene. Okay, C5H10 would be an alkene. If I have singlets, those singlets must be attached to the same carbon. Now, here, there is this carbon can have one of two possibilities. And this is, by the way, this is my process, but this should be your thought process. This carbon must have either an OH, and if it does, then everything else falls into place. Okay, or it must have the double bond. And if it does, again, everything else falls into place. With the only problem being that needs a hydrogen would be that. Now, to know that there is a double bond, you can also take a look at the values. Okay, double bonds are between 4.5 and 6.5, which we're seeing down here. Now, at your level, I would consider either of these two as correct. If I recall correctly, it should be this one. And I will explain why it's not. But before I tell you it should be this one, let me actually confirm it. And this will be our last question. For these, 1, 2, 3, 4. So let me explain why this is the correct one. This, you have these two hydrogens here, and that should mark this as a triplet. Okay? You don't have a triplet here. So you might tell me, Maser, this hydrogen, shouldn't it still be as a triplet, and each of these two, why are they different? Unfortunately, alkenes, so this I'm gonna say, don't, I mean, it's the process that I care about. But unfortunately, alkenes, there's a tendency that the cis and the trans hydrogens protected behave differently. Because, of course, their environments are different. Okay? Since there is no real shift in the double bond. I think they would be cruel to give you this. Okay? In fact, because I'm not a cruel person, let's actually go and do an easy one. As your last NMR question with me. By the way, I will go over, and again, I will send you a video of my answer for the 6 NMR questions I've given you. This time I'm going to go through all the questions. So, 4 and 4, C5H8O, there are only two peaks, so this must be symmetrical, so that there are only two peaks. The peaks are all triplets. Is that not that clear? I'm telling you that, normally they will tell you that in the exam. If they are all triplets, you only have CH2s. Only 5 carbons, and these carbons show that they are, at least that one is adjacent to a C double bond O. And the only way to have symmetrical and CH2s only, the only structure that will contain CH2 only would be a cyclic compound. Okay, so read the information. And if you read the information, then you are going to be on the right track. But read the information. Triplets, therefore CH2 next to CH2, you have two sets. Okay, so the way to do that would be CH2, 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 CH2. There must also be a carbonyl next to one pair. The only way to connect, because there are no other hydrogens, and it's symmetrical, so it must be a bond there. But write it down. This thought process has to be written down.